Hello everyone, welcome to a lecture on microprocessor systems and interfacing. My name is Dr. Vilayat Khan. I'm an assistant professor at Comsets University, Islamabad, VA campus. The topic that I'm going to discuss in this lecture is interfacing memory with the 8086 and 8088 microprocessors. 8086 and 8088 are the two popular members of the Intel family of microprocessors. The slides that have been used in this lecture have been edited from different sources, including the two sources given on the screen. 8086, when operating in the minimum mode and connected with external memory called the real memory and input and output devices, is shown here. So this is the block diagram of 8086 microprocessor when operating in the minimum mode. So here we have the 8086 microprocessor. It is connected with an external clock generator 8284A. This is the clock generator, and this clock generator generates the clock signal that synchronizes the activities of the microprocessor. So the output of called clock of this clock generator and ready and reset, these three outputs of the clock generator are connected with the clock, ready and reset input of the microprocessor. In this mode, all of the control signals are generated by the microprocessor itself. Here we can see the control signals are directly generated by the microprocessor. For example, whether the access is being performed on the memory or the input and output, here this pin generates this corresponding control signal, read, write control signals, and interrupt, acknowledge, and many other control signals are generated by the microprocessor itself. To select that the microprocessor is working in the minimum mode or the maximum mode, the pin minimum maximum pin is used here. So in this case it is connected with the 5 voltage, which is logic 1, so that would select the minimum mode of this microprocessor. Just like the figures we have discussed before, the microprocessor data bus and address bus, which are multiplexed, are demultiplexed using buffers here. So these buffers are used to demultiplex the address and data bus of the microprocessor, because these pins in the microprocessor address and data pins are multiplexed. They are used for sending and receiving data, as well as they are being used for sending the address. So these pins are connected with these buffers, and these buffers demultiplex the address, and then the address bus is connected here, as we can see here. Similarly, the data and the address buses, the data and address multiplex pins are connected with the bidirectional transceivers, and the job of these transceivers is that they buffer these pins, as well as they are responsible to control the direction of the data. So for example, if the data is received, that means that the read operation is being performed, and this transceiver, with the help of this data transmit and receive pin, would select the direction towards the microprocessor. And when it is writing the data out of the memory location or onto the input and output port, then the outgoing direction is set by this transceiver. Here we can see an interrupt controller. This interrupt controller is receiving interrupt request, and then it is sending an interrupt request through the interrupt request pin, which is available as an input pin of the microprocessor. So then the microprocessor then accordingly choose an interrupt handling routine through an interrupt vector, and then interrupt is being handled, or interrupt is addressed. Apart from these transceivers and buffers and interrupt controller, the random access memory is also connected. Here we can see that the random access memory is connected with the control signal here. It is connected with the data bus. It is connected with the address bus. Similarly, the read-only memory is also connected with the control bus, the data bus, and the address bus. And just like that, the input and output devices are also connected with the three types of bus. Note the arrows that here the arrows are bidirectional, so the data is written to the random access memory and it can also be read, while the read-only memory is only read and the data is not written to it. The input and output devices are also written to and maybe read. So the arrows and the bidirectional arrow represent that the data may be written to it and may be read from the input and output devices. When the 8086 microprocessor is operating in the maximum mode, then an additional controller called 8288 bus controller is also connected to the microprocessor. So the minimum mode, maximum mode is selected through the same pin, which is connected to the ground. In the earlier case, it was connected with the VCC. And here it is connected with ground, which is logic 0, so that would select the maximum mode of the microprocessor. So in this mode, the microprocessor is not generating all of the signals directly, but in fact many signals are generated, control signals are generated by the bus controller here. And the three fins, the status fins, S0, S1 and S2 are connected with the bus controller here. And then this bus controller is responsible to generate the control signals. So these control signals are more specific in the sense that they are separate lines for memory and for input and output operations. And the rest of buffers and transceivers and interrupt controller, random access memory, read-only memory, and the input and output devices are connected as usual as it was as these were connected with the 8086 microprocessor in the minimum mode. Microprocessor, whether a simple computer system or a complex computer system, microprocessor-based system will always have memory. Memory is used to store instructions and data for the microprocessor, and these instructions and data then are brought inside the microprocessor and stored in the register array, and then executed by the arithmetic and logic unit of the microprocessor. So almost all systems contain two types of memory: read-only memory or ROM, and random access memory. These are the most popular two types of memory used with the microprocessor. There are a number of other types of these memories. Read-only memory, as the name specifies, is the memory that can be only read and cannot be written to it. So this kind of memory is also called a non-volatile memory. So this will retain the data even if the power is shut down. This memory, as the data is written to it during the manufacturing process in the field and not in the field. Then there is another type of ROM called programmable read-only memory. So this type of memory is not very common nowadays. Here this memory is manufactured in the factory, and then the data may be written to it or in the field using any other ROM programmer, for example, to write the data onto the ROM. And then there is an EEPROM, which is erasable programmable read-only memory. So this data, this ROM can be, the data can be erased and can be rewritten to it. And nowadays, the most popular form of ROM is EEPROM, which is electrically erasable programmable read-only memory, or the flash memory. So data can be written to it multiple times and can be read. This type of memory is normally used to, for example, to store the basic input and output operating systems, BIOS, called BIOS. There are two types of random access memory. So random access memory is the type of memory that is volatile. Whenever the power is shut down, the data disappears from the memory. So this is also called volatile memory, while the ROM is called non-volatile memory. There are two types of random access memory. One is static random access memory. This type of memory doesn't require any additional circuitry to refresh the data, so that's why it's called static. While the dynamic random access memory requires some additional circuit to refresh the data over the random access memory after at certain intervals. So static RAM and dynamic RAM normally are available in small sizes, and this type of memory is a bit expensive than the ROM, but it is faster. So both types of memories, RAM and ROM, are used in the complex computer systems. Here we have the hardware organization of the memory address space. So for example, in 8088 microprocessor, the microprocessor can support 1 megabyte of memory. So the 1 megabyte memory is organized as 1 mega locations, and each location has a storage capacity of 8 bits. So it is organized as 1 M cross 8. So that means 1 mega is the number of addressable locations, and each location can store 8 bit or 1 byte of data. So if we have 1 mega locations, then these are numbered as starting from 0, 1, 2 until the final address. And it is a 20-bit address, so 20 bits are sufficient to address these 1 mega locations uniquely. So the first location is all zeros. In decimal system, it is just 0, 1, 2, and then the final address is F, 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 which is all ones, 20 ones in the binary. So this 1 megabytes of memory is organized this way, that we have 1 mega locations, and each location has a capacity of 1 byte storage. And this memory is connected with an 8-bit data bus that is designated with D0 and D7, D0 till D7. So this is the data bus as in 8088 microprocessor. The database is 8-bit wide. 8-bit data can be read or written at one time. And to address a specific location inside the memory, a 20-bit address needs to be provided to the memory unit, and that 20-bit address is coming from the address bus or indirect from the 20 pins of the microprocessor. And these 20 bits of the address are designated as 0 till A19. So this 20-bit address would identify a location among these 1 mega locations, and then other control signals will identify if a read or write operation is happening on that location. And if it is a read operation or write operation, then the data will either be read or written to that location through this data bus. The memory can be organized in 2 banks in 8086 microprocessor, because in 8086 microprocessor 1 megabyte memory is organized in 2 banks, 2 separate banks. As 8086 microprocessor allows 8-bit and 16-bit data read and write operations, so that's why it is more feasible if the data 1 megabyte data is organized in 2 separate banks. So here we have 2 banks. One is the even bank and the other is odd bank, or one is the low bank and the other is high bank. So the 19 among the 20-bit address, the 19 bits are connected as the address to these banks. So here we have A1 till A19. So these 19 bits of the address are connected to both of these banks. So these 19 bits are sufficient to address each location in among the 512 kilo locations inside each bank. So this bank has 512 kilobytes capacity, this bank has 512 kilobytes capacity, and the total locations inside this bank are 512 kilo, while the total number of locations in this bank are also 512 kilo. So as these 19 bits are connected to both of these banks, so these 19 bits are sufficient to uniquely address all of the 512 kilo locations in both of these banks. And then as each bank has the capacity, every location in each bank is 8-bit wide. So the low bank provides the lower byte of the 16-bit, and they are connected with the D0 till D7 of the data bus, while the next higher byte of the data, D8 till D15, is connected to the second bank, or the odd bank. And then there is a pin called bank high enable pin, which is only available in the 8086 microprocessor, and this pin is not available in the 8088 microprocessor. So this pin is connected, or this is active low pin. This is connected with the select pin of the bank, or chip select pin of the bank. So whenever this bus high bank high enable pin provides a 0, this chip is selected, and the A0, which is the least significant bit of the 20-bit address, which is A0, is connected with the low bank. So these bits can either select both of these bank, or select either one of the two banks. For example, if this is 0, then this bank will be selected. If this is 0, then this bank will be selected, and both of the bits are 0. As 0 is 0 and bus bank high enable is also 0, then both of the banks would be selected. To transfer a byte from the 8088 interface memory system, then let's suppose this is the 1 megabyte memory. So in this memory we have 1 mega locations, and each location has storage capacity of 1 byte. So the 20-bit address A0 till A19 would provide or identify a unique location inside this 1 mega memory, and then data would be written to that location or read from that location through this data bus D0 till D7. And when a word of data is transferred to or from the 8088 microprocessor memory, then we have two banks, as we just saw on the previous slide. So this is this is one of the bank, and this is the other bank. So the 19 bits are connected to both of these banks, and when a word is to be transferred from the memory of the 8088 microprocessor, then sorry, these are not two separate banks, but they are the same. They are just the one bank connected with the 8088 microprocessor. So these are 1 mega locations, and each location has 1 byte capacity. So to read a 16-bit data in 8088 microprocessor, this data may be written in two bus cycles. So in the first bus cycle, the 20-bit A0 till A19 would identify a location, and let's say that location is location X. So the 8-bit from this location would be read or written to it through this 8-bit data bus. And then in the next bus cycle, which is the second bus cycle, the address provided through these 20-bit address lines would be incremented by 1. So it would identify the next higher location, which is X plus 1. And the 8-bit data would be read from this location or written to it through the data bus here. So in 8088 microprocessor, 16-bit data can be read or written to the memory locations in two bus cycles. While in case of 8086 microprocessor, there are two separate memory banks. So for example, if the even addressed byte is to be transferred, then this is the even bank and this is the odd bank. So if, for example, the single byte is to be read or written from the even bank, then the 19-bit provided here would identify a location in this bank and also in this bank, but the bank high enable and the A0 bit would choose only one of the bank, and in this example A0 would be low, so the low bank or the even bank would be selected, so this bank would be enabled, while bank high enable is high, so this bank would not be enabled even if the address is provided to both of these banks in the corresponding location, but only the low bank is enabled as A0 is low, while the high bank is not enabled. So the 8-bit would be transferred to or from the low bank designated from the location designated by or identified by these 19 bits of address. And as D0 and D7 are connected to the low bank, so the byte would be transferred to from or to this low bank through this 8-bit bus. And if, for example, if the odd address byte is to be transferred, and that odd byte transfer means that the single byte of data is read or written to this high bank or odd bank. So the same 19-bit address identify a location among these two in both of these banks, but only one of the bank is enabled. And in this example, this bank high enable is low, so this would enable this high bank, while a 0 is high, so this low bank or the even bank would not be selected. So the byte transfer would happen only from this high bank or odd bank, and that byte transfer would happen the higher bits of data bus, that is they are D8 and D15. So the high byte of data would be transferred from this high bank through these 8 pins, which makes the high byte of the data bus. So we see that the low bank can be read, and 8-bit data from the low bank can be read, and 8-bit data from the high bank can be read, as well as a 16-bit data, which makes 1 byte from the low bank, one byte from the high bank can be read at the same time. Because in 8086 microprocessor there are 16 data pins, and the data bus available in 8086 microprocessor is 16 bits, so that allows or enables the microprocessor to read or write 16-bit data in one cycle, unlike the 8088 microprocessor, where we saw that 2 bytes of data can be transferred to or from the memory in 2 bus cycles, while in this case 16-bit data or 1 word of data can be read or written to the memory in just 1 bus cycle. And let's suppose that the even address word is transferred. That means that the starting address of the memory is landing in the even bank, while the next byte is taken from here. So let's say the address start, the starting address is located or landing in the low bank. So these two locations, location X and the next higher location, which is X plus 1, and that next higher location is in the second bank. So these two locations are identified in both of these banks through these 19 bits, and the data fins are connected to both of these memory banks. So through these data fins, the low byte is transferred, and through the higher data bus lines, the higher byte is transferred to this bank or from this bank. And both of these banks are selected. So a 0 is low, so this would select the low bank, and so this would select the low bank, and bank high enable is also low, so this would select the higher bank. So in this example, the 8086 microprocessors reading or writing 16-bit of data in one cycle. So these 19 bits, A1 till A19, would choose two separate locations in both of these banks as designated by these arrows. The location X and location X plus 1 are selected, and the corresponding part of the data bus with D0 and D7 are connected till here to this bank. D8 and D15 are connected to this bank, and the control signal or chip select pins are low for both of these banks. So both of these banks are selected, and the data transfer would happen. So 8 bit are transferred to or from this bank, 8 bits are transferred to or transferred from this bank. So 16-bit data in total would be read or written to the memory of the 8086 microprocessor in just one bus cycle. So 8088, a similar 16-bit data can be read or written to the memory in 2 separate bus cycles, while here the data 16-bit data can be read or written to the memory in just one bus cycle. Similarly, the odd address word can also be transferred by the 8086 microprocessor. So here, if only the odd address word is transferred by the 8086 microprocessor, then this would take 2 bus cycles. So in the first bus cycle, for example, the microprocessor has to send as an address, a 19-bit address to the memory, and in this first bus cycle, this first byte from the odd bank is selected, and as the corresponding address would identify an even address byte here, so that is not read in this first cycle. Only the byte selected in the odd bank is selected, and this is read through the D8 till D15 data bus lines, and this is provided low, so this high bank or odd bank is active in this bus cycle, while this bank is kept non-active. So this is provided 0 is high, so this is not selected. So the byte is only transferred from this high bank. In the next bus cycle, the address is incremented. The address 19-bit address is incremented, so it will the address will now point the next higher locations in both of these banks, but only the low bank is enabled this time in the second bus cycle. So A0 is low, so this would select the low bank, while the high bank in this example is not selected because the bank high enable is 0, so this bank is not enabled. So the next byte in the next bus cycle is transferred from the low bank. So in this example, 16-bit data was transferred, but the address was started or landed into the odd bank. So to make this kind of read operation possible, to read the first byte from the low high bank, while to read the second byte from the low bank, then this kind of read operation or write operation is possible in 2 bus cycles. To decode or to identify a memory location, the address coming out from the microprocessor needs to be decoded. Because in many cases, even though microprocessor 8086 and 8088 microprocessor is supporting 1 megabyte memory, but it is not necessary that all of the memory that it can support is to be attached with the microprocessor. In many cases, the microprocessor is attached less memory than it can support. So in that case, or in many other cases, when the 20-bit address is coming from the microprocessor, then that 20-bit address should be properly handled for the proper functioning of the memory system. So for that, the address needs to be decoded properly so that the memory systems should be properly selected, and the specific locations inside the memory would be selected properly. For that, some simple decoders are used to decode the memory address, and one of the simple decoder is address decoder is 74LS139 decoder, and this is a 2 to 4 lines decoder. Here we can see the block diagram of this 2 to 4 line decoder. This decoder has 2 inputs, A and B, and then there is a select line represented with G prime. So this is an active low. So whenever G is 0, this chip is selected and it will be working, and these 2 inputs would choose either of these 4 outputs. So whenever an input is provided and the chip is selected, one of these 4 outputs will be low and the other would be high. So here we have the truth table for this, or characteristic table for this decoder. So we have 3 inputs. One is the enable pin and the 2 are the select lines. So G prime, when G prime is high, regardless of the inputs, all of the outputs are high. That means they are logic 1. So Y0 till Y3 are logic 1. And when the G input, which is the enable input, is low, so whenever this is low, this chip is selected, and when the select lines are low, then the first output, which is Y0, is low, and the rest of 3 outputs are high, logic 1. And when this is the 2 inputs, A and B, are 1, 0, 1, so B is 1 and B is 0 and H is 1, then the second Y1 output is low and the other 3 outputs are high. So we can see the diagonal here. So each time the input at these select lines has changed, one of the output is 0 and the other outputs are 1. So that logic 0 output is then used to select either of the 4 banks. At 4 banks are connected to the microprocessor. Here we can see another address decoder that is called 74LS138. So this is a 3 to 8 lines decoder, and in this decoder there are 3 select lines. The one line is G2A, G2B, and G1. So G1 is active high, and the other 2 select lines are enable lines are active low. So whenever we want to select or enable this decoder, G2A and G2B should be 0, and G1 should be 1. So in this scenario, this decoder will be selected or enabled. And when this decoder is enabled and the 3 inputs provided here, or then choose either of the 8 outputs to be active low, to be low, and the other would be high. So for example, here we have the inputs. So we have 3 enable inputs, G2A, G2B, and G1, and we have 3 select lines. So these select lines select one of the 8 outputs. So if G2A is 1, G2A is 1, then this chip is not enabled. So regardless of the other inputs, all of the outputs are 1. And when G2B is 1, so regardless of the other select lines or enable lines and other select lines, all of the outputs are again 1. And when G2A and G2B, regardless of the values of these 2 pins, if G1 is 0, then this chip is again not enabled, and so regardless of the other select lines, all of the outputs are again 0. But when G2A and G2B are both 0 and G1 is 1, and only in this case this chip or this decoder is enabled. And in this case, when the select lines are changed, the output changes. So these, for example, if the select inputs are all zeros, then the first, which is the first output, which is output 0, is 0, and all the rest of outputs are 1. When the inputs become 0, 0, 1, the select lines has the value 0, 0, 1, then the output number 1 is 0, and all the rest of outputs are again 1. And similarly, we can see the diagonal here, and whenever the select inputs are changed, the outputs are changed. So only one of the outputs is logic 0 and the other are logic 1. A typical memory device is given here. So here, this example, we see that it's a typical memory device, and in this memory device, here each memory device has a set of address connections, and these address connections are designated with A0, A1, A2 until AN. So there can be a number of address lines in each memory chip, and these address lines, depending on the size of the capacity of the memory inside. So here we see that the address lines are ranging from A0, A1 till AN. So N is the number of N plus 1 is actually the number of address lines in this memory chip, and each chip has input, output, or just output pins as well, and these output pins are depending on the capacity of the memory, and the capacity of each memory location, or the capacity of data to be written to it or to read from it from the memory chip. So they are O0, O means outputs, O0, O1, O2 until ON. So here we have N plus 1 total output pins, and these output can be just used for the output in case the memory is only read, and these output pins may also be used for writing or reading data in case the memory is read-write memory. And each memory has a write enable pin as well. In this case, it is active low. So whenever the data is being written to this chip, a 0 should be provided through this pin to make the write operation enabled on this memory chip. And also an output enable pin is also present in some memory chips. So this pin is active low in this example. So when a 0 is provided here, the output is enabled, and in that case the data may be read from this memory chip when the output enable is low. And to do any kind of read or write operation, this chip must be selected. So there should be a chip select pin and in this example it is active low. So whenever a 0 is provided through this pin, this chip is selected. So the number of pins, address pins, the number of output pins, whether input pins or input and output pins, or whether they are just the output pins, write enable, output enable, chip select, these are the control signals. These control signals, the number of address pins, the number of output pins, change from chip to chip, and their names in certain chips also change slightly. For example, this chip select may be input G in some memory chips, while in some chip only the output enable is there, the memory cannot be written to it, and in some cases only a single pin is available for both of these output and enable and write enable operations. So the number of address pins needed is here. The number of address pins needed here is directly related to the number of addressable locations in the memory chip. So the more addressable locations inside the chip, the more are the address pins in that memory chip. For example, if the memory chip has 1 kilo locations, and that when 1 kilo in the binary means 1024 memory locations, then for 1 kilo or 1000 locations, 10 bits address pins are required, because 2 raised to power 10 is 1024 in the binary system. And if the memory locations inside the memory chip are 2 kilo, and that means 2048, then these number of locations would require 11 bits of address. So in that memory chip there will be in total 11 address pins, and if the memory locations are 4 kilo, then 4096 are the total locations, and that would require 12 bits. And if the memory has 512 kilo locations, as we saw in the example of 2 banks in the 8086 microprocessor, where each bank has had 512 kilo locations, so 19 bits were sufficient. And if the memory has 1 mega locations, as was the case in for 1 megabyte of memory in the 8088 microprocessor, where all of the memory is organized in a single bank that look like a single bank. Externally, we would we have 1 mega locations in total addressable locations, and that require 20 bits of address. And if the memory locations are doubled, that means 2 mega locations, then that would require 21 bits. So increasing the address by 1 bit doubles the number of addressable locations in the memory. So for example, here we had 1 kilo locations, and that required 10 bits, but when we doubled the number of locations here, 2 kilo, then that required 11 bits, and so on and so forth. And similarly here, 1 mega location required 20 bits, while 20 mega locations require 21 bits. It's a simple example where we have a chip 2716. It's the pin out of this chip is given here. So it's the total capacity of this pin is 2 kilo cross 8. That means it's an EEPROM, erasable, programmable read-only memory. So the data can be read from this chip, and it's the organization of this memory is 2 kilo. That means that 2 kilo are the locations. So you would need 11 pins in total, designated as 0 till 11. So these are the address pins, and it has some control signals. One is power down program pin that is responsible to enable the output. So they are just different program. Power down and program are just different names for the output enable. And here we have chip select pin as well, which is active low. So whenever a 0 is provided through this pin, this chip is selected, and we have 8 output pins, 0 till 07. And the reason is that we have 2 kilo locations, so this number would tell us the number of address pins, and this number would tell us the number of output pins. So 2 kilo cross 8 means we need 11 address pins, and we need 8 output pins. So this is the pin configuration of the 2716 EEPROM, and the total memory capacity of this chip is 2 kilobyte.